Hello, this is Vincent Rolliard from Real Vibrations Systems Developers, and I'm making this short video to give you an introduction to our vibration controller replicators. So we have introduced two optional replicators in our system. One of them is a transient replicator, and the other is a field data or vibration signal replicator. First, I will go through the transient replicator, which is simpler to operate. And what you see here is the main screen of our vibration controller. And to launch the transient replicator, we go to File and Replicators, and we launch Transient Replicator. As it says here, the replicator can be used to generate or replicate classical shocks as well as half-sine shocks or any kind of a short transient burst or complex transient that can be created by the user. So it's a fairly simple system to use. So the first thing is to select what type of a transient to generate. Here we have a half-sine transient, so we can generate say a peak acceleration of 15 meters per second squared. Here the duration is set at 5 milliseconds, so I can change it to say 7 milliseconds, and the digitization rate is 10,000 hertz. And here you will see in the acceleration domain, so all the units are meters per second squared, and we have a feedback accelerometer which is calibrated and with correct sensitivity. And these tails, if you like, before and after the half-sine pulse are important to make sure that the shaker can produce the pulse. The second graph is the expected displacement of a pulse, and this is important to make sure that your shaker can actually produce the pulse given a particular stroke we have. So the shaker I'm using now has got a nominal stroke of plus or minus 30 millimeters, so it should be able to comfortably do this. So the first thing to do is to adapt or to learn, allow the system to learn the dynamic characteristics of the shaker, and for that it generates a small shaker and a small pulse, I should say, and it learns the or adapts to the dynamic characteristics of the system. So now it's learned it, and you can see here the blue curve is a target pulse, and the red curve is a feedback. And now we can produce a number of shocks at will. So every time we click produce, it will generate the shock, and we see the measured shock on the from the red line. This is an artificial system. I don't have a physical shaker connected to my system. I've got a sort of analog simulation of it. But this is really to show you how it works. And the other option is to use different types of shocks. There's some IEC shocks, and the interesting thing here, we can actually produce transients from a file. So the transients can be created by the user, and the manual explains the format of the data. So these are simple text files, and see here I will try and generate some sort of a seismic motion, which is a class C accelerogram, which has been scaled, and the data contains a sampling rate and the units of measurement as well, and also the digitization rate will be adjusted. In this case, I'm not going to go in detail here, but we select the target signal to learn the burst, if you like, of a transient. And also here we allowed a choice as to what parameter of the transient we would like to control. In this case, I will choose the root mean square. And this is the transient we want to generate on the top curve. And below is the displacement. You can see I've got a problem here where the displacement to produce this will exceed my shaker, and I should not generate that pulse. But given I've got an artificial system here, I will artificially increase the stroke of my machine, so to speak, to beyond the 100 millimeters. So here I will learn again the characteristics of a system, of a vibration shaker, by sending this little 10-second burst of transient, and from that it will figure out essentially the transfer function of the system. And it will do so a couple of times until it's happy that it's properly learned the the dynamic properties of a system. Okay, and because I've got an artificial system, I've got a very good agreement between target and generation, and it's doing it for a third time here. So once it's finished learning, we can now produce that burst. So every time you press produce, it actually transmits the signal, the drive signal, to the shaker. That takes, in this case, a bit over 10 seconds, and then we will see the result on the screen. And that's it, and we can do this any number of times. So as you can see, using the transient replicator is fairly simple to use, and the computer is doing all the hard work for you, essentially. So now we can quit this module, exit it, and now I will go into how to use what we call the field data replicator. So the first thing to do is to re-establish the frequency response function of a system. Now, to do this for replication, we need to take a very important step, is to select the identification parameters and make sure that this option here where it says save identification signal is set to yes, because we're going to use these signals to construct filter coefficients for our system. And once we've done that, we launch the shaker identification module and we press start. And now a random signal will be generated, sent to the shaker, and at the same time the response using the feedback accelerometer is measured, and the complete frequency domain characteristics are shown here, where here it shows the magnitude frequency response function. On the right here is the phase frequency response function. Bottom right is the Nyquist plot, which shows you the real imaginary part of the complex frequency response function. And bottom left is the coherence function. And here, because I've got an artificial system, I've got a very good coherence function. But in real systems, the coherence function, frequency response function, will never look as good as this. And normally also for a real system, we will allow this to measure the shaker frequency response function for quite a number of averages. Here I will stop at 9 or 10 because I can. So now all that information is stored. So that's step one. In fact, you shouldn't, if you have a good shaker that is linear and doesn't change a lot, then you shouldn't have to repeat this step very often. So the next step now is to prepare a signal or import a signal that we want to replicate. So for that, we use a field data analysis module. And currently the field data analysis module is set up to exclusively import data that was measured from a saver instrument that is produced by Lensmo. So here I've got a couple of SXD files which were recorded by the instrument, and I will use this one here, which was measured quite recently, a bit last Friday. And this is a reasonably large file, but we will upload the file. And this is not an ideal file to use, so I will make a few more typical files or more suitable files and put it on the web page soon, or send it to clients. And here you can see that the data was recorded, and this is a vehicle traveling on a road. Now, it is very, very important for replication that the signal, the measured signal, is continuous. So there's no gaps in it, and it is very important. Otherwise, well, we're not really replicating anything that is sensible. So once this is done, and you can see here, for instance, that the saver instrument, being an American device, measures vibration in Gs. So here we need to change that unit because we will operate in meters per second squared. So here we can choose rescale data, and we will say it will still be acceleration. We will convert it to meters per second squared, and we'll apply the correct multiplier to convert that. So that now makes that signal compatible with the feedback accelerometer which we have on our shaker. That's basically is done. The only thing I'm left to do now is to select create replicator file. That is important. And I had done this before, so that's okay. I will overwrite this, and now it's creating that replicator file, and it will put it in the correct folder. Okay, so it's done. So now we can quit this, and now the first step, we actually can launch the replicator. We go field data replicator. And it gives us this message on how to do it. So now we say open replicator file, and this is the replicator file that I've just created here. Now these are large files, and it will take a while to upload. Now here, this is an important step. It will ask us if we want to update the bandpass filter. So the signal's already been filtered at these default frequencies. So half a hertz is really to take care of any very long or long period vibrations, and so that the shaker can actually cope with these low frequency vibrations. And also we have a cutoff frequency, which was a maximum frequency at which we measured the frequency response function of a shaker. So that's a very important decision to make here. So if we know, once we've measured the shaker ID properties of our shaker and we look at the coherence function, if a coherence is high, and by high we mean say 95% or 0.95 for frequencies between 2 Hertz and 120 Hertz, then really what we need to do is bandpass that signal to within that frequency range. Otherwise, the replicator will not be able to work properly, or accurately, I should say. So now the signal, the replicator signal that we're uploading is being filtered through that bandpass filter to attenuate frequencies below 2 Hertz and above 120 Hertz. Of course, these values will change depending on what type of shaker you're using. If you're using an electrodynamic shaker, for instance, then you'll be able to have a much broader bandwidth as opposed to servo-hydraulic shakers. So this can take a while because it's, well, it's 60 minutes long. And you can see the file. Now the file is a very strange looking file, and really normally you wouldn't replicate something like that. But let's see what we have here. The top graph is the acceleration waveform of the signal that was measured with that saver from Lansmore. The second time graph is the displacement. And you can see here on the displacement graph you have two sets of line. You have a black line, which tells you what the shaker limits are, the displacement limits, and a pink line, which tells you the shaker limits with a little bit of safety factor. So the setup here, we can set that safety factor to, let's say we set it to 80%. For instance. Oh, okay, well, we'll leave it at 95% at this stage. And we leave it there. Interestingly, on the right, what you see is the average PSD of the replicator signal. We're not going to use PSD in any way here, except to tell us where the energy is with respect to vibration. And this, you will see, is the frequency response function of a shaker. The two red lines are the lower and upper cutoff frequencies of our bandpass filter. If you remember, it was 2 Hertz and 120 Hertz. So now we have an issue here as an example where if we were to replicate that signal, the stroke will exceed the shaker displacement or shaker limit. So what we can do here is we will check and correct excessive displacement of a shaker. So essentially what it will do, it will trim the data where the displacement exceeds the shaker limits. And again, depending on the nature of a signal, and the length of a signal, the duration of a signal, that might take some time. But this is an important step if you want to avoid causing damage to your shaker. I will, over the next few days, create a shorter and more sensible replication file, which I will distribute so that you can set up your shaker more easily. So now the bottom graph is the new acceleration that has been trimmed to accommodate this displacement. And you can see here it's been changed. And here, of course, we can use a little zoom tool here to, if we wanted to explore and investigate a bit further what this signal is about. Okay? And so there's all kinds of options that you can employ here. So now we're ready to go. And then we select go to replication. So there's one more step to do. And now we've detected that the field data was collected at 2.5 kilohertz, whereas the shaker ID test or measurement we just did a few minutes ago was done at 1250 hertz. So the system will automatically resample the field data to match the frequency of the system, the controller. And again, that can take a little while. So that's been resampled, and there's one more step which maybe in the future we'll try and avoid, is to prepare the signal. So now there is some processing going on to basically set the memory ready to go, and also it's going to measure the background vibration on the shaker to give an indication of the nose floor of the system as a whole. And that will help in deciding whether the replicator is supposed to work or not. So here we see where we are. We see that red vertical line on the bottom graph, which tells us this is a start. So as soon as I press start here, the replicator will go. And the top graph will show the 2 seconds, a moving window of 2 seconds, showing you the target signal and the feedback signal, or the replicated signal. And now it's moving. And we can see we got very little vibration at the beginning. And one of the important features of this replicator system is that we can pause at any time, we can resume, but importantly, we can actually move anywhere along the length of a signal to replicate a particular section. So if I right-click on this, on the bottom graph, and I select jump to specific time, I can, for instance, go to, where do I want to go? Let's say I will go here, at about 21 minutes. Okay? And you will see the red, well, I didn't want to go to 20, maybe I wanted to go to 20 minutes. So I can trial and error, do this, and you can see the cursor is there. So now when I press resume, it will actually replicate the signal from here, which we think is a handy little feature. And now it's starting, and you can see the signal here. And we'll actually zoom that graph. And we can see, in this case, quite clearly what the replicator is doing. And in this case, of course, because we have a near perfect vibration system, it's doing a very, very good job of it, of course. For a real system, it will never be as good as that. There is a zooming, I think that's right, we can zoom vertically only by dragging that mouse up and down, so we can set the scale. So we can see the red line actually tells us where we are. So we take that off and we pause it. And let's say I want to go to 45, say 47 minutes. And we'll see the cursor here, and I'll set my scale to 10, that's okay, resume. And I use the cursor to set my vertical scale to plus or minus 10 meters per second squared. And that's it. So it's a fairly simple system to use once you take the right steps, and hopefully it works as well as this when you try it on your own shaker.